I guess we should probably start. Just waiting a minute more. Okay. Good morning, everyone. So I'm Julien Grall. I've been working on ARM virtualization for the past four and a half years. I'm working with ARM since last year on combining the ARM port with Stefano Stabellini. I think one of the biggest features we miss on Xen ARM today is PCI. Before going on what we should do on ARM for Xen, for PCI, I think it's worth to start looking on how works PCI on ARM. This is a quite small schematics explaining how the components work together. So you have the PCI connected to the root complex. You have the IOMMU behind any writes to the memory. So anything should go through the IOMMU, and you have the interrupt controller on the sides with the MSI doorbell probably in the interrupt controller, which, as you can notice, goes through the IOMMU. I will go in a bit deeper just in the next few slides in the different things. So that's roughly how PCI is interacting with the other components of the subsystem. The first thing that we care is root complex. There is not only one kind of root complex on ARM. There is multiple ones. There is some that is ECAM compliant. So ECAM compliant is each configuration space has its own address space. So even if ECAM is there, people decided sometime to do some ECAM-like compliant. By ECAM-like compliant, I mean that it's following mostly the PCI spec, but sometimes it's diverging a little bit, which means that you can't have a generic driver for all this host bridge. You will have a specific driver for this platform. On the last one I've seen, I would say the custom way, because they don't use ECAM, they use maybe indirect access. They use their own way to do the access to the configuration space. So this makes it a bit tricky to do what we want to do on ARM, what we want to do in Xen, because we don't have one single host bridge. We may have multiple ones. So where to put them, how to handle them. Second thing, so you have the access, and then on the sides, when you look on embedded, often you have the clock to configure, to initialize. You may have external device to initialize, etc., etc. Which means that if we decide to put that in Xen, we will have to pull the host bridge, the clock, external device, on potentially other things, which makes potentially like merging Linux in Xen. It's not, I would say, it's not really possible and feasible. When you get the host bridge, then PCI do often, so you have legacy interrupts, which is on ARM usually SPIs. You have also MSIs. MSIs can be distinguished in multiple combinations. So you have the doorbell. So the doorbell is where the device will write the payloads of the MSI. You have the payload. So the payload is something specific to the MSI controller. So it can be the event ID specific to the device. It can be an index for an MSI, etc. The last thing is the sidebound information. So by sidebound, I mean it's something that you can't configure. It's in the hardware, and it will be carried with write of the MSI. So it's often a combination of the device on the MSI controller, depending on the memory path. This could help the sidebound, for instance, to protect the writes in the MSI doorbell. So this information is from the hardware, so you can't tamper it, and you are sure that this device has written to the writes with the right information. So you have MSI, you have host bridge, and now you want to protect, because when you give a PCI to a guest, the guest will have a different address space, and you want to make sure that the guest is only writing to the this address space. Same for the PCI. You don't want the PCI writing in DOM0 or on Xen. So usually you use IOMMU for that. In the ideal world, the IOMMU protects every memory access. So it protects DMA access to the memory regions, and it also protects MSI writes. So on ARM, all the MSI are usually treated as DMA writes. So this means that if you don't map the MSI doorbell in the IOMMU, it won't work. That's going to write somewhere else, or is that going to this is going to break because the address for the doorbell is not mapped in the IOMMU, so you will receive a fault. But as I say, this is the ideal world. In real world, there is still some platforms that, okay, they decided to have some address. It's address specific to the platform, which may not reach the IOMMU. What does it mean? It means that the root complex say, oh, this looks my address, I will keep it and stay here. That's two implications for a guest point of view. It means that if the guest is writing is a guest physical address, which should have been translated by IOMMU, the root complex will think this is a physical address. So you first need have a direct mapping between the physical address and the guest physical address. The second thing is maybe you have peer-to-peer access, maybe can be trapped by the root complex. This means that you can't prevent, without some features like ACS in PCI, you can't prevent access between two PCI, which means what's the security here? What should we do on Xen to be able to prevent writing in MSI doorbell you don't want, or writing in a peer-to-peer, preventing a device to write peer-to-peer. So this could be probably something at the beginning. If you don't have support for ACS, maybe in a per platform option saying this platform doesn't support peer-to-peer, so this is fine to pass through the device. The next thing is, so this is the hardware. No, you want to boot Xen, you want to boot a Linux on the platform, and you want to discover what's on the platform, what has a PCI, what has the host bridge. For that, we use Firmware Table. So the Firmware Table are provided by EFI or by U-Boot. You can find in it what is the host bridge, if it's an ICAM compliant, if it's a specific host bridge, the interrupt controller, the MSI controller, the IOMMU, and the IO topology. By IO topology, I mean how everything is tied together. So where this host bridge, which IOMMU is tied to an host bridge, or what's the sideboard information for the interrupt controller, how to configure the IOMMU. So ARM we support two different firmware tables, ACPI, which is usually quite focused for servers, and device tree, which is a mix between embedded and server. I think people can wonder what's the difference between ARM and x86. This is PCI, so likely this is going to be the same. I think one of the main differences is on x86, the address space is standardized. So you know where is the MSI doorbell, you know where is the memory, you know quite a few things. On ARM, this is not standardized, which means that you can have a board which boots have all the RAM above 4 gigabytes, or you can have a board below 1 gigabyte. So this is not properly standardized. You will have to look at the firmware table to see what it means. So this also means that if you have a set of address which are bought, this is platform specific. This is not, you can't say for all the platform, this will be only this range. The second thing is MSI are usually treated as DMA writes, which means that you always have to map the MSI doorbell in the IOMMU. And the last thing is that on some platform, this is not like, as I was mentioning about the IOMMU bypass, is on some platform you have MSI which may bypass the IOMMU or some set of specific address which aborts before reaching the IOMMU. So this is, I think, the main difference between x86 and ARM. So on Xen we already support pass-through for x86. There is two different solutions. I would say there is a PV solutions. I will go with a slide just after, and there is a QEMU solution for HVM. Let's start with the PV drivers. This is a roughly idea. It's not everything, and I think it would be quite many things in it. So the idea of the PV is PV solution is you have a PV backend and a PV frontend, which is used for accessing the configuration access space. So every time the guest wants to read the configuration access space, it will go through the PV drivers, which is talking to the backend, and DOM0 on behalf of the guest will do the configuration access space or may sanitize beforehand. On every access to the bar of the PCI will be done directly. So we map the region to the guest. In the case of HVM, we use QEMU to emulate the road complex. So we're trapping Xen every time you want to access the configuration space. Sorry, in this case, the guest has a real host bridge, so it doesn't know that it will be trapped by Xen. It thinks that it's directly driving the host bridge. So every time that you're accessing the configuration space, you will go trapping Xen, then forward to DOM0. DOM0 will handle it in QEMU, and QEMU will do the access on behalf of the guest, and then back to the guest. So this is a two-way for x86. What do we want on ARM? I think we have a specific set of things we wanted to try thinking, do we want PV way, do we want to use QEMU? And before doing that, we have a set of requirements, what we want to do. So one of the things on ARM is we don't have only Linux, Windows. We may have multiple OS on the side that are used, that may be custom for your platform, for embedded. On those OS, people may want to just use the OS from bare metal and directly putting Xen as a guest without modifications. This means that maybe PV is not the solution here, what to do. We want to avoid modifying too much the guest. The other thing is we want to take advantage of the firmware table. As you saw previously, there is many things we describe in the firmware table. We describe the topology. You may have multiple MSI controllers, even for the guest. You may have multiple host bridge for the guest, depending on how you want to set up if you have different platforms, etc. So it looks like we want to take advantage on the firmware table for having a better integrations with the code existing in Linux. So the first thing that has been proposed 2 years ago was using PV drivers. Thing is, it was so, as I mentioned, using PV drivers means modifying the host. And the second thing is the suggestion was, it was focusing on a specific hardware, specific platform. And here what we want to do is something that's, it's not about a platform, it's not about an MSI controller. As you may have noticed, I won't speak about a specific MSI controller like the ITS for ARM or the GigV2M or Xilinx MSI controller. I just trying to focus on architecture requirement, what the architecture requires, on trying to provide a way for for explaining how to integrate an MSI controller if you have a custom one, or how to integrate your host bridge. I'm not saying this should be done for this specific host bridge. The second thing we wanted to focus is on trying to address the goal I just said before, no modification in the guest, on also trying to get use of firmware table as much as possible. So the proposal for ARM is moving the host bridge emulation in Xen. Two things for that. When you look at the PV drivers is mostly for configuration access. Emulating an ECAM is fairly easy. That would be the same thing. Second thing is it makes easier for the guest. The guest doesn't have to know its PV drivers. We can start to move some part of the host bridge control in Xen. Maybe at some point thinking about removing DOM0 in the PCI world. I mean, in the handling of PCI Passthrough. Also, in the case of the current proposal, what is being suggested is to still keep it DOM0 for the moment on the loop for any scanning, because I'm still not convinced that we can move all the scanning in Xen. There might be some bits that might be too complex to move in Xen. Also, if you have an host bridge that is a bit tricky, containing clock, etc., it's not yet clear whether we want to keep we want to move that in Xen, because that may be pulling a lot of code, or leaving that in DOM0 on having potentially a communication between Xen and DOM0 to do the configuration that takes place. We started the proposal end of last year. I've sent a second version on the mailing list end of May. This is containing mostly, at the moment, all the things for registering PCI, on explaining the rationale behind the proposal, which means that I'm going through explaining everything about how MSI controller will interact with the PCI, how this is interacting with the IOMMU, on explaining what's the different constraints depending on the platform. I just put a link here at the end if you want to look at the design. So I think it's quite important for us to get feedback from many people as possible, saying this design looks good, or maybe this may not work for your platform, for your use case. So yeah, feel free to comment, feel free to suggest other way, and we can see having a really good PCI Passthrough supporting Xen. Yeah, this is the end of my talk. Is there any question? Yeah, I don't know why is the microphone. Okay.
I had one question about the MSI doorbell.
Yes.
I mean, I think that, well, the thing that you say that it's kind of a problem, that sometimes the MSI doorbell, well, a write to the MSI doorbell doesn't go to the IOMMU. But I think that at the end you always want to map it to the real one. I mean, I'm not really sure what you would want the IOMMU to change the address of the MSI doorbell to somewhere else in memory.
Well, the problem is at the moment the guest memory map is fixed, which means that if the doorbell is not going through the IOMMU, we need to carve out this region from the guest, preventing to put memory in that place. Because if you do a DMA with a physical with an IPA, so IPA is the guest physical address, is the ARM term. You would this would be a catch, by the root complex, and you won't be able to reach the real memory region at the end.
But probably when you do pass-through, you want to have a memory map that's kind of similar to the memory map of the host?
Not really, because this, so in a longer story, you may want to live migrate without PCI device this to another host, to another platform. This other platform may have a different set of address that may not be trapped. So if you use the memory map of the host, you can't know whether all the address has been covered for the next platform. This is a longer story. This is maybe in a 2 or 3 year story where you may want to migrate between 2 different platforms, or maybe 2 revisions that doesn't have the same memory map.
So you basically would like to use the IOMMIU to place the, well, I mean the MSI doorbell may be anywhere in the physical memory, and for your guest you would always like to place the MSI doorbell in the same guest address on all the platforms.
In the ideal world, yes, having a place. So as there may be maybe 2, 3, 4, a certain number of MSI doorbell, we will have to map everything in the guest. So my idea was maybe to have a place in the memory layouts to say this is all where the doorbell will be. I admit that I'm not sure what to do there, because it would be nice to get something, I would say clean, on using just a guest memory layout and not to care about the host, but it looks like to me this is going to be difficult. If you think about the migration story after, that's going to bring some headache to people that will work on that.
So one of the issues we found on Linux was that the I/O virtual addresses coming into the root port will not be forwarded by root ports if they overlap the range of the MMIO addresses going in the other direction. So, x86 has also fixed this by reserving that range. And so now Linux on ARM also, there's a patch which has been merged that says that if the MMIO regions that the root port forwards are these, then reserve that in the SMMU allocator saying these have to be reserved because the root port won't forward. So if your guest address map is not the same as the host, and if it was the same as the host, then Linux would just do the right thing, right? It would know to reserve it. But if it's not, I think it's okay if you're not using SMMU in the guest, if you're not showing it in SMMU, because then you can show it as a reserved memory or something, and the guest just won't try to pass that as a DMA address. But when we get to using an IOMMU in the guest also, that problem becomes trickier. How do you tell the guest not to use that address as a DMA address? And x86 may have solved this.
I may let Andrew answer on this one.
So this is fundamentally a problem with PCI Express, the way it behaves. What has happened is with changes in the spec to introduce access control services in the PCI Express switches, which allow the hypervisor to instruct that behavior not to occur. Realistically, the only solution is to use some newer PCI Express chips, trying to work around this by telling the guest that there are various reserved regions. That works fine if all of your devices are behind one bridge. If you've got devices behind 2 separate switches, you can get into positions where it's impossible to do that.
I think we're talking about slightly different things. ACS, forcing everything to go upstream takes care of the problem of peer-to-peer, right? Where the root port or some downstream switch may see some address, which is an I/O virtual address, hasn't gone to the IMMU yet, and it can just forward it out. That's a different problem. I understand that and how ACS solves that. what I'm saying is something else. Root ports will not forward a DMA address if it overlaps the MMIO addresses that it sends in the other direction. So it okay, okay.
The first version of the spec that had that in was ambiguous, and there was an errata correction to it in the following version of the spec. But yeah, ACS should cope with with DMA going in both directions through the IOMMU and through the root bridges. That's not to say that all of the chips implement it properly. There are a rather large number that don't. A couple of them do have workarounds. There are hidden debug registers where you can basically cause debugging behavior to occur, and everything all the clever logic gets turned off, and that actually works moderately well when you want the IOMMU to deal with everything. Any other questions?
Okay, thank you. I think there is one last question from Ponis.
Well, yeah, so this is not necessarily a question for you, but generally, like, would x86 folks be happy to use kind of a new PCI proposed pass-through mechanism? Is that something that makes sense?
Putting a root complex emulation inside of Xen is what I'm working on for x86 right now, so you can basically reuse all that on ARM. Well, you will have to add some architecture-specific hooks, but yes, the code I'm writing is generic code in principle, and I've tried to extract everything that's x86 specific inside the x86 file, so you should be more or less able to reuse, I think, most of that, probably. And the problem is not really the root complex emulation, that's very simple. The problem is adding all the hooks that you need to trap accesses to the things that you want to prevent the guest from accessing. I mean, the root complex, as Julien said, it's very easy to emulate. The problem is all the different capabilities and hooks that you need to add to the config space.
I don't think your design addressed what kind of root complex you're going to show to the guest. So, like QEMU shows generic PCI host controller, and that.
I think I've said ECAM. That would be an ECAM generic host bridge. I don't see any reason to expose something more complex to a guest.
Okay, and so you're expecting that, let's say it's a Linux guest, and it would just be the generic host bridge driver that
yes,
would work.
I don't see any reason to try to expose a fancy host bridge to the guest. I think we should keep simple as possible, making it easy for anyone to use it in their bare metal OS if they want.
Okay, makes sense.
Any other questions?
Okay, thank you for listening.